Hello again. After the break, I'm going to discuss the liver and glycolysis relationship. One major function of the liver is just to deliver the glucose to the blood by a glucose phosphorylating enzyme, the glucokinase, whose Km for the glucose is sufficient higher than the normal circulating concentration of glucose. Is only related to 5 millimolar concentration. And this feature of the hepatic glucokinase allows the liver to buffer the blood glucose, and after meals, when we have got a high blood glucose level, liver glucokinase is significantly active, which causes the liver preferentially just to trap and to store at the circulating glucose. So we have got when high glucose level, then glucokinase is just said to be active. Other glucose supplies in the body are listed in the slide. When blood glucose falls to very, very low levels, tissue such as liver and kidney, which contain glucokinase but are not highly dependent on glucose, do not continue to use the glucose supplies that remain available. And at the same time, tissues such as the brain, which are critically dependent on glucose, just continue to scavenge the blood glucose using their low Km hexokinase, and as a result, their viability is going to be protected. So glucokinase does not efficiently work when blood glucose falls to very low levels. So the regulation activities of them are said to be different, and hexokinase 1, 2, or 3 are just said to be allosterically inhibited by a product, the glucose 6-phosphate accumulation, whereas glucokinases are not available in this case. They are not inhibited, And we have got another pathway, gluconeogenesis, that is also another important pathway in the degradation of, in the biosynthesis of carbohydrates, not degradation. If we have got some glucose deficiency, if under fasting conditions or long periods between meals, the liver is just stimulated to provide the blood with glucose by means of the gluconeogenesis, and the levels of glucose produced during gluconeogenesis is not available to activate, not enough to activate glucokinase, allows the glucose to pass out of hepatocytes and into the blood. So we can see that gluco means sweet, again, neo means new, genesis to generate. We are going to generate new glucose sources. That means to generate new glucose sources, okay? This is the glucose providing pathway. So in the regulation of hexokinase and glucokinase, the latter one further just ensures the liver accumulation of glucose stores during the times of glucose excess while favoring peripheral glucose utilization, and when glucose is required to supply energy to peripheral tissues in general. And if we just imagine the phosphohexose isomerase, we got the second reaction, and the second reaction of glycolysis is an isomerization in which glucose 6-phosphate is converted to fructose 6-phosphate, and the enzyme catalyzing this reaction is just said to be phosphohexose isomerase, and this is known as phosphoglucose isomerase. This is one of the simplest reactions when you compare with the other reactions. So we have got more important reactions such as the first reaction, third reaction, and the last reaction, the pyruvate kinase reaction. In phosphohexose isomerase, it is freely reversible at normal cellular concentrations of the two hexose phosphates, and this thus catalyzes the interconversion during the glycolytic carbon flow and as well as during the gluconeogenesis. So the phosphofructo-1 kinase or phosphofructokinase 1, the other name, we most frequently use the name, the second name as well, or shortly we call it PFK1. This is the third reaction of glycolysis, and it is the most important reaction of glycolysis. It involves the utilization of a second ATP to convert fructose 6-phosphate to fructose 1,6-biphosphate, and it is catalyzed by 6-phosphofructo-1 kinase, and it is better known as phosphofructokinase or PFK1. And this reaction is not readily reversible because of its larger positive free energy, and the delta G is just said to be plus 4 5.4 kilocalories per mole in the reverse direction, and nevertheless, fructose units readily flow in the reverse gluconeogenic direction, and because of the presence of the hydrolytic enzyme fructose 1,6-biphosphatase is the reverse enzyme. When we imagine the gluconeogenesis, we have to think about this fructose formation, the glucose formation by means of gluconeogenesis. But in the glycolysis, the name of the enzyme is phosphofructokinase or PFK1. In gluconeogenesis, we call it phosphofructokinase 2 or PFK2, or we call it fructose 1,6-biphosphatase, F1,6-biphosphatase, fructose 1,6-biphosphatase, or shortly F1,6-biphosphatase. So the presence of these two enzymes in the same cell compartment just provides an example of a metabolic Fuchai cycle, which, if unregulated, would rapidly deplete cell energy stores. So we can see that there is a thing that we can use this enzyme once more or not. There's a debate about this. But in evolution, it is used. So this enzyme is used. So it is a Fuchai cycle. A utility takes place. So not Fuchai, we can call it as Fuchai in general. But there's still a debate about this. So the activity of these two enzymes is so highly regulated that the PFK1 is considered to be the rate-limiting enzyme of the glycolysis, and for fructose 1,6-biphosphatase is just considered to be the rate-limiting enzyme in gluconeogenesis. We got aldolase. Well, this enzyme is able to catalyze the hydrolysis of fructose 1,6-biphosphate into two 3-carbon products, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, and aldolase reaction just proceeds readily in the reverse direction and being utilized for both glycolysis and the gluconeogenesis. And if we just think about the triose phosphate isomerase, the two products of the aldolase reaction equilibrate readily in the reaction catalyzed by triose phosphate isomerase. Succeeding reactions of the glycolysis utilize the glyceraldehyde 3-phosphate as a substrate, and thus the aldolase reaction is just pulled in the glycolytic direction by mass action principles. So the glyceraldehyde 3-phosphate dehydrogenase shows us that the second phase of the glucose catabolism just features the energy-yielding glycolytic reactions to produce this ATP and nitrogen dichloride reducing form. And the first of these reactions, the glyceraldehyde 3-phosphate dehydrogenase, just catalyzes the nitrogen dichloride oxidase-dependent oxidation of glyceraldehyde 3-phosphate to 1,3-biphosphoglycerate and nitrogen dichloride reduced form. And the glyceraldehyde 3-phosphate dehydrogenase reaction is reversible, and the same enzyme catalyzes the reverse reaction during the glyconeogenesis. If we just think about the phosphoglycerate kinase, the high energy phosphate of this 1,3-biphosphoglycerate is used to form ATP and 3-phosphoglycerate by the enzyme phosphoglycerate kinase. That is the only reaction of the glycolysis of gluconeogenesis that involves ATP, and it is reversible under normal cell conditions. So this is just associated with the phosphoglycerate kinase pathway. This means that it takes place in the erythrocytes, and we have got the reversible reactions, the formation of 2,3-biphosphoglycerate reaction by the enzyme biphosphoglycerate mutase. And this 2,3-biphosphoglycerate is an important regulator of hemoglobin's affinity for the oxygen. So we have to note that 2,3-biphosphoglycerate phosphatase degrades 2,3-biphosphoglycerate to 3-phosphoglycerate. It's a normal intermediate of glycolysis, and this 2,3-biphosphoglycerate shunt then operates with the expenditure of 1 equivalent of ATP per triose passed through the shunt, and this process is not irreversible under the physiological conditions. We start with half glucose, then glyceraldehyde 3-phosphate is available, 1,3-biphosphoglycerate to 2,3-biphosphoglycerate, 3-phosphoglycerate, and we obtain pyruvate at the end. We have got the phosphoglycerate mutase and enolase. These are the other enzymes that we can see remaining reactions. They are aimed at converting the low energy phosphoacyl ester 3 phosphoglycerate to a high energy form and harvesting the phosphate as ATP. Okay, let's have a break.